Welcome, Python developers and data scientists. Grab a seat, because in this explainer, we're unlocking some massive parallel processing power. If you spend your days wrestling with heavy numerical computations, you already know that performance is literally everything. So today, we're going to explore a tool that is fundamentally changing how we approach data science and scientific computing in Python. We've all been there, right? You write this clean, elegant NumPy code, but as your datasets inevitably swell from megabytes up into the gigabytes, your execution time suddenly stretches from seconds to minutes, long enough to go grab a coffee, come back, and just sort of contemplate your life choices while you wait. You've hit a wall. Your CPU, no matter how beefy it is, simply can't process massive parallel matrix operations fast enough. Well, enter CuPy. Think of it as your GPU-powered hero. It's built specifically to take that familiar NumPy syntax you already know and completely turbocharge it by running it directly on your graphics card. So here is our roadmap for this explainer. We're going to escalate your mastery level by level. First, the GPU upgrade. Second, mastering memory. Third, crafting custom kernels. Fourth, concurrency and sparse data. And fifth, performance optimization. Let's jump in. All right, starting off with section 1, the GPU computing upgrade. Look, before you start throwing massive arrays at the GPU, it is absolutely crucial to do some basic hardware environment checks. You can't just cross your fingers and hope for the best. You really need to verify your CUDA device presence, ensure your CuPy version actually matches your runtime, and critically, check your GPU memory availability and compute capability. Understanding your hardware-specific constraints right out of the gate, that's what separates the pros from the amateurs, and ensures your code isn't going to just randomly crash halfway through a massive multi-gigabyte matrix multiplication. The crazy thing about CuPy is that it acts as NumPy's identical twin. You literally just import CuPy as CP instead of NP, and you're off to the races. But the performance difference? It's staggering. When we benchmark CPU-based NumPy against GPU-accelerated CuPy for large matrix multiplications and fast Fourier transforms, or FFTs, the latency just drops off a cliff. We're talking about reducing execution time by orders of magnitude for heavy mathematical workloads. And the best part? You get all of this without having to learn a totally new syntax. Moving right along to section 2, mastering GPU memory. You know, one of the biggest bottlenecks in GPU programming isn't actually the math itself. It's moving the data around and allocating space for it. CuPy solves this beautifully with a highly efficient memory pool. Instead of constantly asking the GPU operating system for new memory blocks, which honestly is a painfully slow operation, CuPy's memory pool aggressively reuses previous allocations. It intelligently manages the lifecycle of your data, totally preventing your code from stalling out while it waits for GPU memory to free up. And what about when we need to play nicely with other libraries like PyTorch or TensorFlow? Usually, moving data around means passing it back to the CPU, which instantly ruins your performance. But here, DLPack is an absolute game changer. It's an open standard for in-memory tensor structures. By using DLPack, we achieve what's called zero-copy data exchange. That means your arrays stay right there on the GPU memory, seamlessly transitioning between NumPy, CuPy, and your deep learning frameworks without any of those expensive transfer delays. Next up, section 3, crafting custom kernels. CuPy gives us some incredibly specialized tools to write our own GPU operations, specifically distinguishing between an element-wise kernel and a reduction kernel. So if you need to perform a highly specific, robust distance calculation independently on every single item in an array, you'd use an element-wise kernel. But if you need to collapse that entire array down into a single value, like calculating the L2 norm across millions of data points, you'd reach for a reduction kernel. CuPy compiles these on the fly, so you're getting native CUDA performance but with Pythonic ease. Okay, but what if you want total, unapologetic control? For the ultimate flexibility, CuPy provides the raw kernel interface. This literally lets you write actual, raw CUDA-C code as a Python string and launch it natively. Imagine computing something deeply complex, like a Mandelbrot set fractal. With raw kernel, you define the exact grid sizes, and you control the custom thread and block dimensions to perfectly match your GPU's architecture. It is the ultimate escape hatch for optimization. Which brings us to section 4, concurrency and sparse data. So here's a crucial point to remember. Your GPU is a massive parallel processor, and you really shouldn't let any parts of it sit idle. By using CUDA Streams, we can manage multiple workflows simultaneously. Imagine we have two entirely independent large matrix multiplications. By placing them in separate CUDA streams, CuPy tells the GPU to run exactly two operations concurrently, side by side. If your hardware has the capacity, this effectively cuts your processing time in half compared to running them one after the other. And let's be real, real-world data is messy. It's rarely a perfect, dense block of numbers. CuPy isn't just for basic math. It's packed with highly optimized tools for advanced scientific workloads. It can effortlessly generate and manage sparse, compressed sparse row, or CSR matrices, where most of the values are zero, which saves a massive amount of memory. It can solve complex, large, dense linear systems essential for physics simulations, and it can run high-speed Gaussian filters over huge image arrays. It does all of this by leaning into the sheer throughput of the GPU.
Finally, Section 5, Profiling and Performance Optimization.
If you really want to optimize, you have to measure accurately. But here's the trap. Standard Python timers like time.time just do not work for asynchronous GPU calls. Python is going to think the operation is done the very second it sends the command to the GPU, completely missing the actual computation time. Using Python to time a GPU, yeah, that's kind of like using a sundial to time a drag race. It just doesn't work. To fix this, we have to use event-based profiling. By recording specific CUDA events right on the device itself, we capture the true, highly accurate execution time of large operations, totally independent of any CPU lag. Another incredible optimization tool in the CuPy arsenal is just-in-time, or JIT, compilation. Just look at this step-by-step pipeline to see how seamlessly it works. First, we write a standard mathematical function in Python, like a Saxby kernel, which is short for scalar alpha x plus y. Then we just decorate it with cupx.jit. CuPy takes that and compiles the Python code directly into machine-level CUDA instructions. We manually launch this kernel, define our grid sizes, and then verify the output to make absolutely sure we didn't sacrifice correctness for our new blazing speed. Okay, check this out for our grand finale, kernel fusion. When you run multiple array operations normally, CuPy has to read from memory, compute the math, and write back to memory for every single step. It adds up, but by simply adding the @cp.fuse decorator right above your Python function, CuPy combines all those separate operations into one single fused CUDA kernel. It reads the data once, does all the math in the super fast GPU registers, and writes it back exactly once. This drastically eliminates memory overhead and drops latency to the absolute minimum. We have covered some incredible ground today. You've seen firsthand how to elevate your code from a simple drop-in NumPy replacement all the way to writing fused, highly optimized custom CUDA kernels. And you get to do it all while staying right in the Python ecosystem you know and love. You now possess the keys to unlock profound parallel processing capabilities. The tools are literally in your hands. Your environment is prepped, and the GPU is waiting. So the only question left for you is, what computational bottlenecks are you going to crush next?